Hello everyone, I'm Satyam, and in this final project, I explored how different machine learning methods have been working with handwritten digits from the MNIST dataset, especially when we reduce the size of the data uh, using techniques like kernel PC and Laplacian eigenmaps. The MNIST dataset has digit images as 784 dimensional vectors. That's a lot of data. So I tested how well models perform before and after reducing that number to just 30 features. So in the problem one binary classification, for my digit 3 was a digit 6, which were my assigned digits. I started with a binary classification task using support vector machine, once with a linear kernel and once with a Gaussian RBF kernel. As you can see in the results, the linear SVM actually performs slightly better, achieving precision and recall. This tells us digit 3 and 6 are linearly separable. So a simpler model worked great here. In problem 2, here we can see that next I used SVMs to classify all 6 assigned digits. I tried both 1 versus all approaches. Surprisingly, one versus all slightly performed in both precision and recall. So that's a strategy I would take moving forward. Moving to problem 3, so this is the what I images got. So here I ran k means with different cluster counts. K is equal to 4, 5, 6, and 8. The cluster visualization showed that k is 6, gave the best separation, which makes sense. It matches the number of digit classes. You can actually see that each cluster center looks like a different digit, which is pretty cool. And in the problem 4, clustering, so I also applied hierarchical clustering using both Euclidean word and Manhattan average distances. So the dendrogram shown that Euclidean plus word linkage gave much clearer, well-separated groups. Cutting the tree at 6 clusters aligned really well with the actual digits. Uh, then moving to problem 5, kernel PCA 784 dimensional into a 30 dimensional, which is the conversion I do from a 784 dimensional to 30 dimensional. Then I applied kernel PCA using a polynomial kernel to reduce the data to just 30 features. While linear SVM saw a slight performance drop, the RPF SVM still reduced accuracy 98.33 and accuracy which is impressive. So it achieved an accuracy of 98.33. Clustering also worked really well in this reduced space. Structure of the digits was preserved. In Laplacian eigenmaps, which is the problem 6 lastly, I used Laplacian eigenmaps, a graph-based dimensionality reduction method. This method does a great job preserving local structure, and it showed up the results. My RBF SVM hit 99.17% accuracy, which was even better than kernel PCA, and clustering was also sharper and more distinct. If you look at the eigen plot, you'll notice a nice elbow over here. Uh, like for the problem 6, if we move to the eigen plot, both kernel PC and Laplacian eigenmaps came very close, with Laplacian doing the best among reduced methods. Going to the final takeaways, I would say that dimensionality reduction helped reduce complexity and training time, and Laplacian eigenmaps like gave the best accuracy while preserving digit structure. Mm, as you can see over here, and in every clustering method, k is equal to 6 was the magic number. It aligned perfectly with the actual class digit. This project really showed me how powerful it is to combine dimensionality reduction with models like SVM and clustering, and like with SVM and clustering algorithms, and it makes larger data set more manageable without losing the meaning inside. Thank you for watching the video.